Hey guys, Donald Trump here, and thank you so much for letting me into the White House. Now today, we're going to be doing the second episode of Do Your Work and Don't Be a Jerk. Now in today's episode, we're going to make revision great again.
What are you doing? What are you doing? What's he doing? What's he... That's my class. They're my They're my students.
Well, yeah, I have a very busy schedule. I have a wall to build.
They're my students. Oh, awkward. Alright, in your assessment you'll be asked about hardware. You'll be asked to define some key terms. Happens in most examinations. Define just means write about, say what it is. What is a CPU? The first thing to do when you get an acronym is actually say what the acronym stands for. There's a mark. If you say the CPU is the central processing unit, there's a mark. Okay. It says that it contains the control unit and the arithmetic logic unit. They are two parts of the CPU. We will look at them in more detail in the future, but the control unit controls the flow of information inside the CPU, the flow of data inside the CPU, and the arithmetic logic does all of the maths and the logic inside the CPU. But acronym CPU stands for the central processing unit. It contains the control unit, it contains the arithmetic logic unit, and it's where all the processing is done. What's a core? A core is a processor. So if you have two cores, you have a dual core processor, you've got two processors. Quad core, four processors. The clock speed. Inside of the CPU, inside of the computer, there is a clock, and it is measured in hertz. A hertz is 1 per second. So a clock speed is measured in hertz, and it controls how many fetch execute cycles is conducted within that time frame. So the more clock pulses, the faster the clock speed, the more fetch execute cycles your computer can do, the faster your computer is, or the faster it will operate. Cache is high-speed memory used by the CPU. It is really close to the CPU, therefore it's faster to access because it's closer. The data, we're talking very small amounts here, but the data doesn't have as far to travel, and that makes a massive difference when you're talking about the speed of calculations that a computer needs to do. The cache is relatively small. It just holds the instructions that the CPU is going to be dealing with next, or common, frequently used instructions. So the CPU can access it from cache, which is fast, rather than pulling it from RAM, just slower, or the hard disk, which is really slow. Even if it's solid state, it's really slow. The CPU does not want to run out of instructions. If the cache runs out because it's too slow, or if it's not big enough, the CPU will run out of instructions. It will start pulling from RAM. Your computer will slow down. Everybody's favourite, perform 8-bit binary addition. Okay, we have an example here. In binary, 0, 0, 1 is 1. We don't have a 2, so we do 1, 0, and 3 is 1, 1. We will go over that again in lessons near the exam, but if you can't work out why, if you can't remember why, you're just going to have to memorise it. 2 is 1, 0, 3 is 1, 1. Okay, so in deanery, in decimal, in everyday maths lessons like you did at primary school, 0 plus 1 is 1. So 1 is the same in binary as it is in pretty much every other number base. 1 plus 0 is 1. 1 plus 1 is 2. I find even simple maths like this, I find it easier to do it in denary, in decimal, and then translate it to binary. Otherwise, as I've seen students just get confused and get mixed up over very simple calculations. So 1 plus 1 is 2, which is written as 1 naught. Not 1, not 10, 1 naught. So we say 1 first, then the naught. So because we say the 1 first, that's the one that we carry. 1 naught. Do you see that? Do you see how it's written down in the same order? 1 naught. We carry because we can only put one digit, binary digit, bit value down. Naught plus 1, the carry is 1. 1 plus 1 is 2. What was 2? It's 1, 0. So we carry the big number, we carry the 1. 1 plus 1 plus 1 is 3. So that's 1, 1. So again, we carry the 1. 1 plus 1 is 2. And 1 plus 1 is 2. Got a problem here. We've run out of space. So 1 plus 1 is 2. So that's your answer. But there's an overflow. We've got 8 bits. Our answer has given us 9 bits. That's given us an overflow error. You will need to revise DBMS. DBMS stands for Database Management System. You will notice that the DBMS sits in front of the database. So if you want to access a database in this situation, you would have to go through the DBMS. So an app, a desktop program, a web site would go through the DBMS, and then the DBMS would access the database, pull the data out. Why does it need to do that? There are lots of different reasons, as you can see on your screen. A DBMS is very useful for a database is just the data. So when you load a database up in a program, you're not loading a database up. The database is just the data. It's just like in your Python assessment, you have words and numbers separated by commas. And that's it. That's the database. That's what a database is. It's just data separated. It's a persistent store of data. Remember that one? It's a persistent store of data. So what a DBMS does is it reads that data and it does stuff with that data. For example, it generates reports. It allows you to search, run queries, filter, that kind of thing. It allows you to do validation. You can see on the screen other things that it allows you to do. You will need to be able to explain, identify user interfaces. The most common one, which you'll use on probably a daily basis, is WIMP, Windows Icon Mouse Pointer. Used by Apple, Windows machines, Linux. You can use icons on Linux machines, and it's really useful. It's got pictures, so you don't need to be an expert. You can just click on the picture. It's got a mouse, a keyboard, typically visual representation of what you are doing with icons. Menu interfaces were very popular, very common with early computers because they didn't have the graphical power to display icons. And they are really popular again, especially with things like apps on mobile phones, because you haven't got a keyboard, you haven't got a mouse, you just want something simple, you just want to tap something simple and get into the information quickly. Same with if you've got an Xbox, or if you've unfortunately got a PlayStation and you're using your controller to access the menu. You don't really want to be able to type into it. You don't want anything complicated. You just want a series of options and you just drill down. Command line interface, CLI, you've done some work on Linux last year where you type directly into it. It can be a pain. It can be a pain. You need to know the exact commands. If you get it wrong, you have to spend ages looking them up. And it's just, if you're not an expert, it's really awkward and really inconvenient. If you are an expert, it's really fast, really accurate. You don't have to load all of the graphical user interface, so your computer will run faster. And you can run it on older computers. You can make old computers do really complicated things by just ditching the graphics and just using a command line interface. Input and output devices for users with specific needs comes up frequently. Here you see I've got an example of a screen magnifier. You may think of a screen magnifier as, you know, in the accessories that you might mess about with that make the screen larger. But that's not a device, that's a piece of software. I've given you an example of a screen magnifying device, which is just a magnifier. But also, as well as not being able to read the screen, you can get voice synthesizers. A piece of equipment, like a musical piece of equipment, you can plug into something and it will synthesize the sound and output it through a speaker. These are amazing. On the bottom left, you'll see the Braille printer. It punches raised dots into the paper, so somebody who can understand, can read Braille, they rub their fingers over the Braille printout and they can read it, as you would have seen in possibly Braille books, Braille novels. The one on the right is really interesting, the Braille reader or Braille display. So if you want to read something that's on an electronic device, this thing has a series of pins. Remember those things that you used to get as a kid and you used to put your face in and take it out and it would leave the impression of your face in the pins? I imagine it to be a bit like that. And it dynamically changes. So if you're reading something on an iPad or something like that, or a menu or any kind of electronic device, you rub your fingers across it, and when you've rubbed your fingers across it, it'll change the pins for the next line. And then you just dynamically run your fingers over that and it'll dynamically change again and it'll just keep updating itself. It's pretty clever. An actuator, you see these connected to robots. Typical example is if you can't move your arms or you haven't got the strength to lift things, these things can be programmed at various different strength settings to enable people who haven't got a full range of physical movement to extend that physical movement or to replace their physical movement. Encryption. You need to know what encryption is. You need to be able to describe it. Currently with Python, you are not encrypting, you are compressing. You are taking something that's really long, a sentence, ask not what, and you're making it into something smaller, a list of unique words and a list of numbers. You've compressed it. If you look at the file size of the original text and your numbers and your unique words, the file size may be smaller. We're only talking about one sentence. Certainly if you put in the complete works of Shakespeare and run that through your Python program, the two files or the single file that you would output with your unique words would be smaller, would be a lot smaller than the complete works of Shakespeare. But you haven't changed it. You can still read it. I can go into your text file and I can still read the text in there. Encryption prevents me from doing that. What you typically get is a key. If you look at the diagram, you've got some plain text. The key is a digital key. It's an answer to a mathematical question. And then you run it through an algorithm and it converts, in lots of complicated ways, it converts your text into something that's indistinguishable. Now, to get it back, you have to run it through that algorithm again. But you need the key, you need that unique long list of numbers to put into the algorithm. If you put an encryption key that's slightly different into the algorithm, it'll decrypt it or it'll attempt to decrypt it, but you won't get the same answer back because the encryption is calculated based upon that key. So to decrypt it, you need that key. And by key, we mean a big long list of numbers that we use in our mathematical calculation somewhere. And that's exactly what happens when you go to eBay or Amazon.com and you log in, or even Facebook, if it says HTTPS, and you log in. You don't want to be sending your password in plain text over a network, over Wi-Fi, or over the school network or something like that. You want it to be encrypted. So there'll be an encryption algorithm, there'll be a key, so the encrypted text is sent over the network. So if somebody does pull that encrypted text out, they can't do anything with it. It's just meaningless without the key in the algorithm. Acceptable user policy. Back in the day when we had planners, we had the acceptable user policy in there. AUP, acceptable user policy, it does exactly what it says on the tin. What is acceptable in your organisation? When you're at school, when you work in an office, wherever, when you buy your self-driving car in a few years' time, you will have to agree to one of these. It's not your computer at school. It's not your computer when you go to work in an office. It won't be your computer at college. It's theirs. And they think that you need to behave in a particular way if you're going to use their equipment. You may think that's reasonable. You may think that's unreasonable. It's theirs, so you don't have a lot of choice in the matter. So, acceptable user policies. Generally, it's a mixture of courteous, common sense, professional behaviour and security restrictions, advice, precautions. So you see the list here. Not give out personal details, be polite, don't send anything offensive. And then we've got some security things thrown in there as well. Only open emails that you're expecting. Don't open attachments that you don't know who they're from. Don't spam people, don't download programs, don't try to install things. Only use the internet for work purposes. No cyber slacking. Never heard that one before. Cyber slacking. I like that. No cyber slacking. What is the difference between off-the-shelf and custom-written software? So, off-the-shelf is general-purpose software. It's been written to suit the needs of as many people as possible, and you can't change it. Off-the-shelf is a term that was invented before the internet, so it applies to downloadable software as well. You can't change it. Custom written software is written generally for one client or a few clients, and it's written to exactly meet their needs, which I'm sure you can imagine is really quite expensive. If I paid someone to make Microsoft Word, that would be a lot of money. That would be a lot of money. Whereas if millions of people buy Microsoft Word, the development costs are spread out amongst the client base, and we get it for 40 quid, 60 quid, whatever it is. This is when software is run. I'm going to say it. I don't want to say it. I don't want to say it. I'm going to say it. It's when software is run in the cloud. I hate that expression. There's no such thing. I absolutely hate that expression. It's not in the cloud. It's in a computer server farm in the desert somewhere in America. It's not in the cloud. It's just another computer at the other end of your broadband cable connection thing. Okay? And what happens is that computer runs the software rather than yours. A very good example is if you log onto your school email and then you go into OneNote. OneNote is running on the Microsoft server, and you're seeing the web version of it. You're seeing the result of it. So if you click on something, if you insert an image into the web version of OneNote, the Microsoft computers are doing the processing. They're cropping, they're resizing, they're moving the image around. Not your computer. Your computer's just displaying a web page largely. Now that has a number of advantages and disadvantages. First of all, it's cheaper for the school or the company that you work for, or you at home even, because you don't need a powerful computer. You just allow their computers to do the processing. If you work for NASA or a huge university and you've got some really complicated calculations to make, but not that often, you don't want to be buying a huge supercomputer for £20 million. Why not just rent the Amazon servers for 5 seconds every week? It's much cheaper. Amazon wins because they get your money. You win because you don't have to buy a supercomputer. Now, we've been talking about validation recently. Validation is a computer check-in that user input is sensible. It does not check whether it's right or wrong. It checks whether it's sensible, whether it's within a range. So you can check whether it's between particular values. You can check whether it's characters rather than numeric. You can check whether it's a particular format. Okay, logic gates and truth tables. Really simple. We've done them loads of times before. Let's have a look at what they are. You'll see I've got a diagram here. I've called this input A, this input is B, and the output from whatever this thing does is X. Now this is an OR gate. It's got two inputs. If this one is on, or this one is on, or both of them are on, and that's the bit that people forget, or both of them are on, then there is an output. Okay, this is what the truth table looks like for an OR gate. A is this, B is all the possibilities of this, and X is all the possibilities of what happens when you feed A and B in. So for example, one option is we could have them both off like we have now. A or B. Is A on? No. Is B on? No. Are they both on? No. So the answer is 0. Okay. Nothing going in A, nothing going in B, nothing comes out. Now, to fill in the rest of the truth table for A and B for the inputs, if you can count in binary, count up in binary, and that way you will not miss a combination. You won't miss a combination. If you can't count in binary, you're just going to have to work out which ones are on and which ones aren't on. So I can count in binary, so I'm going to count in binary, and I know that these are all of my possible options. So what happens when A is on, sorry, A is off, or B is on an OR gate? A is off, B is on. Well, that one, or both. So that one or that one. It gives us a 1. It gives us an output. The other situation, what happens if the other one's on? Well, logically, it's exactly the same thing. They're just in a different place. What happens if they are both on? Well, remember I said that one, or both. Gives us an output. Let's have a look at the AND gate. Here's one I prepared earlier. So again, we can pre-populate A and B, the inputs, by just counting in binary. Or if you're convinced you got the one next to it right, you can just copy off that for inputs. That's just what goes in. That's not going to change. What comes out? Why? Well, an AND gate works if that one and that one are on, and no other situation. So it only works if that one and that one is on. You could have many inputs going in. It would only work if they were all on. So these are all zeros. It's an AND gate. Oops. A NOT gate is an inverter. There are only two combinations to go in, on or off, because there's only one switch. So off, on. And it's an inverter. It inverts, it flips, as you can see. Now this circuit is a little bit more complicated. The trick to multi-level logic diagrams, logic circuits, is to break it down. So let's have a look at what we've got here. We've got A, B, C, P, Q, R. So what's going on? Look at the gates. We've got an OR gate here. We've got A and B going into it. So ignore everything else. We are just concerned with this section here, A, B, P. So we've got A, B going through an OR gate, and whatever happens, the answer is P. Underneath it, we've got C going into a NOT gate, and the answer is Q. Then our circuit takes the answer P, takes the answer Q, whatever that is, and it feeds it into an AND gate. And when these are both on, it lights up the light, it produces an output. Incidentally, gates like these are used for doing complicated mathematics inside of a computer. This is how a computer does maths. But we don't need to worry about that. What we need to do is solve this truth table on the right, and it looks really confusing, and I often see students just take this and then they think they need to do something with 0, 0, 0 to produce P, which isn't the case. Remember, we're breaking this down. Let's have a look at this again. We've got AB going through an OR gate to give us P. So we're only bothered about AB to give us P. So AB is an OR gate, so it's that one or that one. So ignore this C column. So, in fact, can I hide it? Yes, you can. So, nothing, nothing. There's something there. So if there's something there, if there's a 1 there, we get an output. Now let me put that back, because you can't hide it in paper. You can't hide it in your exam. But that gives us that. Now, C is not, and then gives us Q. So in other words, Q equals not C. So Q equals C knotted. Now I'm not going to hide it this time because I want you to follow it. So Q is the opposite of C. So that's going to be a 1, a 0, a 1, a 0, a 1, a 0, a 1, and a 0. So it's that. Knotted. Now that only leaves us with R. What is R? R is P and Q. So in other words, when these are a 1, so the only time that they are ANDed is there, and there, and there. So the rest must be zeros. Okay, so A or B gave us P, C knotted gave us Q, and then those ANDed gave us R. Break it down to make revision great again.